So today we are going to finish topic 1, which is stereoisomer. Although I covered how to assign R and S last week, that was just for the purpose where in nomenclature questions, the most common mistake is you forgot to assign R and S. I will still reteach you how to assign them, so you have a better concept of learning stereochemistry. And the other target is we are going to make your first flashcard. So on that's not covered by discussion menu. If we got the time to do that, we are going to do it. So hopefully, just from my notes, your first flashcard should be this one. If we got time to do it together, we do it together. If we don't, then you know where to find the completed notes, right? You all know? Okay, stereoisomers. In week 1, we talk about why we need to draw a wedge or dash. Examples like molecules, because bonds, especially our carbon bonds. I don't use picture card, just you all can see bonds. It wedge out and it can dash in. That's going to make a difference. People didn't know that for a long time, and that's why the things showing on screen is one of your week 1 exercise. Just we give you a formula, then you draw as much conformers or isomers as you can. So that was one of the exercise. However, the isomers that we are going to teach today is different from the exercise you did in week 1, which we are basically talking about the scenario where you can see they look very similar to each other. Okay, so these four sugars, oxygen, hydrogen, carbons, they are in the exact same place. Unlike the previous exercise you did, it can be just I put carbon on number 1, number 2, or number 3. I put oxygen on number 1, number 2, and number 3. No, in the example that we are going to discuss in stereoisomers, carbons and the oxygens, they're all bound to the same, but just the only difference is whether this bond is wedged out or dashed in. So you can see the example showing here. As I told you, R and S was part of the nomenclature. See how the correct way of name something. For each stereocenter that's present in the molecule, you need to give them a R or S, give them an assignment, right? Okay, they have the same name. If we don't talk about R and S, just from the things you learned last week, they all have the same name, even the same position number. However, the only difference is their R and S. Make sense? So we're going to, these 4, definitely 4 different molecules. Although it looks very obvious here, but people, real people, didn't know that for decades, and that caused serious problems, especially if you don't know the difference between R molecule and S molecules. Well, in later we are going to talk about they also have other names, but you might be more familiar with this L or D. So you might heard of some of the drugs are named under L, some of the drugs are named under D. So that causes problems, especially if you use them in real case, like use them on humans, patients. Okay, but anyway, people pay for a lot to realize that these 4 are actually different. So that's why we teach stereoisomers in the beginning of the organic chemistry. All right. So if we need to discuss, just focus on whether the wedge or dash changes differentiate on how that's going to affect a molecule, then we need to first learn a word, chiral, which is the one that I highlighted here. Okay, chiral center. This carbon, this yellow carbon, is bound to 4 different groups. Okay, only if a carbon is bound to 4 different groups, then it is named a chiral center. So the 4 examples on the left, they have at least one of the group are the same with the other. So all of the 4 examples are achiral. The example that I was showing above only the chiral center you need to assign R or S, okay? All right, so let's move on. We are all talking about a chiral center or a stereo center, okay? Okay. Now here is an example that compound A is different from compound A prime. If you just watch, on discussion menu, you just draw it out, but I think that's not very obvious. So I still want to, this time I will use projector. So these two. So you can see they all have the same color. They all have the same atoms. These three, okay, white, purple, blue, are all bound to the same. But the only difference, if you just think about from the plane of the view, blue is wedged here, or blue is dashed here. So if I do it this way, or either way. Okay, so from now on, we are done. So the molecules that we are talking about in this discussion is the relationship between molecules like this, where they have exactly the same, but they are different. So now it's very obvious they are different, right? Okay, all right. Okay, so compound A is different from compound A prime. And we keep moving, okay? How people realize compound A is different from compound A prime is because they shine light. So that's come to a special kind of light, polarizing light. Okay, polarized light. So polarizing filter is a kind of filter it looks like a glass slide, but they have they only go in several directions. For example, they are all vertically parallel, okay? And if you insert this special polarizer in front of the light, then only the lights that are parallel to the direction of this polarizer will go through and shine those parallel polarized lights on your sample. And people start to shine polarized lights on R molecule or S molecule, okay? And then they rotate the filter, rotate the polarizer slightly. Only under certain angles they can see the molecule. And then if the lights just keep moving, then the molecule will disappear from the microscope. So that's how people realize these two are different, because R show in a certain angle, for example alpha, and L, well the other one, S molecule, show a different angle. So only when the polarized rotates to a different angles, then they can see the other molecule. So that's how people figure out these two are actually two different compounds. Okay. However, that's coming to individual chiral molecules. Okay, so we call this optical activity, which means all individual chiral molecules can be observed under the polarized light. But if I mix R and S molecule with 1-to-1 ratio, so this is we give them a name, racemic mixture. If they are 1-to-1 ratio and they're the same, I'm talking about a pair of R and S molecule, and you mix them 1-to-1 ratio, they will cancel out each other. And in that case, you won't see molecules, so they won't behave optical activity. Okay, so that's just a concept, and also a history of how people realize R or S, which is the letter we used in nomenclature. In the past, it was also named under positive or negative, or D or L. So those were the past name of R and S. But now we all consistently use R and S for stereocentric. Okay? All right. Now let's move on. So up to here, it was not related to how you are going to be tested in the quiz. Okay? Now it starts to. In discussion 2, we teach you guys, we talked about Newman projection, okay? And here is the second projection, Fisher projection. Fisher projection is, we only have 2. So Fisher projection is something Professor Nasri probably haven't covered in her lecture, but it's kind of tricky. theoretically, as long as we have teach you, we have taught about stereoisomers, then you should be able to do this. But it actually takes many 118 students a long time to master these skills, to transfer, okay? So it's fine if you cannot do it today. Just exercise on that, and we might not throw question with feature projection in the quiz or exam soon, because we know it's a harder thing, and it is just for you to know this skill. Okay, we'll give you time to increase your skills on transferring, okay? So feature projection, the trick is on all the vertical lines are dashed. All the horizontal lines are wedged out, okay? So the examples are showing here. So how to remember this? Or can you do the other way? No. So how to remember this? You can imagine all the horizontal ones are hugging you, so it's wedged out, right? Wedged out, so it's hugging you. All the horizontal ones are hugging you. So that's how you remember this, okay? Why people use feature projection, okay? So if you, let's go to the picture card, okay? We basically use it when we have a linear chain like this. And just like the example showing on discussion menu is a vertical line with 3 carbon in a row, right? So people doesn't want to draw out wedge or dash all the time. Especially many of the cases, they are all stereocentric. So people consistently use wedge, use feature projection to show that they are wedge. So I'm not sure if this is a better visualized way. I'll see if I can move them. So you probably can't see it. So that's not the best angle. Okay. So will you be able to see? This is how feature projection is written. That it's crossed. So horizontal bond are hugging. Could you see that? No? Okay. So as long as the molecules are, so it's the same if we have more, right? As long as the molecules are written in feature projection, they will line like this. They will line out like this. Good? So maybe this, yeah. So it's almost a straight line, and horizontally they're all wedged out. This one should be like this, okay? Yeah, much better, okay? Okay, so later, since if I do the projection, I cannot show the picture time. Okay, later in the exercise, in today's, in the exercise of week 4 discussion, you are going to assign RNS in the case like that. I know you can draw wedge or dash bond, but the best way to transfer it, like you still want to draw it maybe in wedge dash, like a bond angle, like normal way you do it like this, okay? So how you transfer, I'm going to write the transfer process on paper, but I want you to view the process first. Initially it was right in the vertical way, then you choose one side to transfer. For example, if I choose the side that my hand is in, then you are going to write whichever bond that is facing your hand, facing your eyes, wedge, because you are basically observing like this. Okay, so when you are transferring, you are observing like this. Make sense? Okay, so whichever bond that is facing you, which is my hand here, is wedge. Whichever that is farther from your hand is dash. Whichever that is in the main line of the horizontal, they are just solid line which is on the plane of the paper. We are going to draw this process on paper, but this is how you visualize it. Good? Okay. And another thing, because it's all single bond. In discussion 2, we also talk about single bond, you can do free rotation, right? Which means I can also, I can put in whichever way I want. You guys are closed book exam, and you also cannot bring any models to the exam, which means in the exam, if you also want to do some transferring, like sometimes you think drawing the group wedge will be most benefit for you to see it. Remember we talked about RNS last week, that when you assign R or S, you need to put the least priority group in the back of the paper. What if the least priority group is in the plane of the paper, and you don't have a model, your hand is the best model, because you can always mimic the bond, like 1, 2, 3, with your hand, okay? And maybe use this will be better, okay? So this is the yellow, maybe use blue, okay? The blue atom is my arm, and the rest of them, purple is my thumb, and the rest of them are like that. If you want to do rotation, you can always do rotations with your hand. The other hand also works. So your hand is the best model. Okay. Hopefully I don't need to use picture cam again, but that's something that's later we are going to use. So I don't transfer back and forth between picture cam and projection. Okay. All right, here we were just talking about the horizontal bonds are hugging you and how you transfer. Let me choose the second one as an example of how you transfer. So you are here, okay? So if you transfer to that one, so how you do it? So you are here. The hydrogen is closer to you. So when you are drawing the bond, well, first I'm drawing the main line, which is the vertical line, because CH3 is dashed into the paper, okay? So this hydrogen is close to you, so it's wedged out. And the other side hydrogen is also close to you. And this bromo is far away from you, so it's dashed. Okay, bromo. Okay, chloro. Okay. Okay. So that's how I transfer. Why it is different from the structure that is drawn on the discussion manual? Because single bond can do free rotation. This why they put chloro in wedge, because they rotate. So use the arm. You can rotate. Because if I project here, I cannot show. So think about now. Chloro is dashed into the paper. From your perspective, my thumb would be chloro. Okay. From your perspective, hydrogen is wedged into your side, right? And CH3 and the main line is my arm and this one. Okay. So what do? You rotate this. So if you rotate this, I want the chloro to be wedged, which means my chloro is thumb from your perspective, because it's dashed in just from the one that I was drawing, right? So you just rotate. So now chloro is facing you, and you just keep in mind which was the original one, and then just draw them out. Make sense? Does that make sense? Okay, so that's how you transfer. Because our ultimate goal of this step is to assign RNS, which means you always need to put the least priority group in the back of the paper. It's fine if just with wedge or dash. If just with wedge or dash. With this one, I have students just with this. They can assign easily. They can imagine, okay, if I watch from with certain angle, I put the least priority group in the back of the paper, that they can assign. But I know most of my students, they prefer this way. So that's how you do it. So do whichever way to assign RNS. Okay, I just give you the tools. It's your choice to choose which method to use. Okay, did I make this point clear? Yeah.
I'm probably missing something, but with the free carbon bond rotation, if you're allowed to rotate it between drawing the two different forms, then what's the point of specifying which direction things are pointing in?
Well, because
oh wait, no, I
you got it.
Because you can't just change.
Yeah, you cannot change how you.
That's the whole point.
Yes.
Okay, I see.
Okay. Does his question sound good to? Did you guys understand what he was asking? Good. Okay. So we were changing the rotation, but we didn't change the sequence of which bond is bound to, which group was bound to carbon. Okay. That's the point of RNS. We changed the rotations, which means this one always go after this one. But we didn't change, I didn't change the position between these two. Okay, if you have question on that, we will come to that afterward. Okay. All right, so after you have assigned RNS, you are going to facing the scenario where in one molecule or a pair of molecules, there are more than one stereocenter. Okay? Here on our discussion menu, the ones that you guys were exercised on in the week 1 was constitutional isomer, which means they have different arrangements. Well, the oxygen was even not bound to the same carbon in that case, which is not under the case that we are talking. We are talking about stereoisomers, which are these 4, okay? I don't like reading, but I highlight some, okay? Their relationship are they superimposable? Are they mirror image? Just by combination of these two, we are going to see they can be a pair of enantiomers, okay? This one, okay? Or they are actually the same molecule, or they are a pair of Derosers, or they can be methyl compound, okay? In the discussion menu, they spend 2 pages on teaching you how to differentiate the relationship between these 4. We will walk through this first. I have a better way to differentiate, but you need to go through the normal way first, okay? So how do we assign? Okay, in normal way, you either draw the mirror image. So compound A, okay, feature projection. Okay, starting now, you are going to start to assign RNS for every stereocenter you see in this type of question. Okay, so both of them are S molecule. Both of them are S stereocenters. Okay, and compound B is actually the mirror image of compound A. And if you draw them out, these 2 are R stereocenters. So in the definition of enantiomers, superimposable and not mirror image, okay? So if these 2 are mirror image to each other, but if you copy and paste this part, I mean, B doesn't look the same as compound A. So that means B is the if you just opposite this one opposite compound A, it looks like B, which you can see. Bromo, it was on the left now, on the right now. Bromo was on the left. Everything is opposite, but these two cannot just overlap on each other. So that's enantiomers. Well, you can see I really don't use this method, okay? Derosers are something, if you just compare the stereocenter, SS with this one is SR, okay? Well, if I'm continue on this, that's the table here, okay? Are they superimposable? Are they mirror image? So that table describes their relationship. But even just the time that I was walked through this example with only 2 stereoisomers, I'm confusing myself. So definitely, that's the definition, but we don't use this. Which one I use is the sentence I sent actually on last week's notes, but I think I also said it on this week's note, okay? Only if all the stereocenters are opposite, they are a pair of enantiomers. As long as one of the stereocenters are the same, they are a pair of Derosers. Does that sound much easier? You don't have to compare the mirror image or kind of thing, right? Okay, let's check if that works. Okay, so A and B. First thing, you need to make sure they are stereoisomers, which means bromo is bound to the same carbon, OH is bound to the same carbon. And then SS, they're all opposites, RR, right? Okay. A and C, I see the same as stereocenters. So as long as one of the stereocenters are the same, they are a pair of Derosers. Is that much more easy now? So you don't have to compare, right? Okay, then is there any exceptions? Because remember, we have 4, right? I was only talking about enantiomers and diastereomers. They're the other 2. Well, identical is the same, which means these 2 are actually the same molecule. Methyl is a special one, which is on the next page. Okay? These 2 are methyl, because they are also opposite. They all have stereocenters opposite to each other. Okay, and they're also a pair of stereoisomers. But why? What's the difference between enantiomers and methyl? Is the mirror image superimposable on the original one? From my perspective, which means this G prime was actually the same molecule of compound G. So if you do the mirror image, they overlap on each other. Okay. My way of differentiate this is if I assign all the stereocenters and they are all opposite to each other, I need to check if this is a symmetrical molecule, because usually methyl group are symmetrical. You can see. Usually they are symmetrical. So I need to check if there is a symmetrical plane in the molecule. So how do I differentiate the relationship between these 4? First, let's see if they are exactly the same molecule. We might draw it in different ways. For example, I draw one of the molecule in normal way and the other in Fischer projection. You might be confused, but these 2 are actually the same molecule. So that's identical. So they're actually the same. And then you assign R and S. If all the stereocenters are opposites, then you need to check if there is a symmetrical plane. If there is, that might be a methyl, pair of methyl groups, a methyl compound. If there isn't, then this is a pair of enantiomers. Doing all the stereocenters, as long as they're one of them, they are the same. These are a pair of diastereomers. Okay. So your exercise. Okay, I have taught you how to assign R and S last week. We will go to some exercise for it, but there is a mistake in the discussion menu, and it's also a good example to play with. So I want you guys to do this one in the class. So what's the time? Okay, good. Now it's 6:37. I'll give you 2 minutes. Okay. I know I just need a letter, but I also want you to exercise on transfer the Fischer projection to the normal way. Do it. Okay, I'll give you until 6:40. Okay. All right, what's the relationship between? So your answer key in the back of discussion menu of this one writes methyl. It's not correct. These 2 should be a pair of diastereomers. Okay. You can choose to assign R and S just on this Fischer projection, but I will still work through the whole process of transferring back to zigzag. Okay. So first thing, all the horizontal ones are hugging you. They are wedged out. So you write in this format, like the one I just showed with my arm. Okay, that's the first step. The second step is you choose a side. For example, I choose the left side to watch, okay, then my hydrogens are all wedged out. Okay, my hydrogens are all wedged out. And my cyano groups are dashed in. Okay, they are dashed in. All right, so you do the same with the other one. Then you will have these 2 compounds. Ready? You can assign R and S, or you can use the way that I teach you just like a minute before. So you can rotate. So here, if you really doesn't want to compare, you can rotate. Okay. So this is if I rotate this side. Okay, this ethyl group is here, and this cyano group is here. Okay, because I'm in opposites of your directions. So this, my arm, okay, now my arm is the horizontal solid line. And from your perspective, ethyl is wedged out. So this is my ethyl, okay? And my thumb is the cyano group and the hydrogen is dashed in. So that's from your perspective, right? Now if I rotate my cyano group, which is my thumb, now it's in the plane of the paper, okay? If I rotate it in the back, I rotate my ethyl group, which was wedged out in your perspective into the plane of the paper. That's the one that I was drawing on the other side. So if you draw this, it will look exactly the same as the group that I was showing here. See, this side is the same with this one. And then you do the rotation of the other side. You will figure out this hydrogen is dashed in, while this hydrogen is wedged out. So even you don't need to assign RNS, you can differentiate. This one is opposite, in the opposite stereocenter of that one. Well, the right carbons are the same. They have the same sequence, so that's the same stereocenter. So as I told you, as long as there are one stereocenter are the same, they are a pair of Derosers. Okay? Good? Yeah, question.
Can you explain one more time how you got from the second step to the third step?
The green arrow?
Yeah.
Okay, so you choose a side to look. For example, I choose this. Okay, and then the first thing you do is you draw the horizontal line in the plane of the paper. Because so remember, previously it was shown like this. Now you are watching it like that. Okay? You draw the horizontal line in the plane of the paper. And then which side that you choose to watch. Okay? For example, the one that's showing here. Okay, okay. Now the yellow one are the hydrogen, probably from your perspective. Yeah, from your perspective, the yellow one is the hydrogen. Now, if you choose to watch the molecule from this side, okay, then you transfer this. The hydrogen, yellow hydrogen, is wedged out. So on the molecule I write in the third step, hydrogens are all wedged out. So your observation point perspective was from watching this to watching this. Make sense?
Mm-hmm.
Good. Okay, so as you can see, you have a page of exercise like this, and that's something you should go for it. Feature projection is one of the hard questions, and it's also because this one we have a wrong answer in the discussion menu, so I use this one as an example. The rest of them, that's the exercise. Okay, good. Okay, let's come back to my note. Okay, some tricky things. Okay, after that one, I think this should be an easy one, right? So assign RNS for these two. Of course, they are opposites. You see, because the OH is dashing in and OH is wedged out. But there's something I want to teach you. So assign, yeah. Assign RNS for this one. All right. So the first one should be easy because I already put hydrogen, which is the least priority group, in the dash position, which means it's in the back of the paper, right? So whichever direction it is, then it is. If it's counterclockwise, it's X. Okay. The second one, hydrogen, which is the least priority group, is not in the back of the paper. It's actually wedging out. So just from what I teach you, you can rotate. Use your hand to rotate until this hydrogen is in the back of the paper. Of course, that's method one. But there's an easier way to do that, which is think about this molecule. Think about this molecule. From your perspective, okay, this molecule is showing from your perspective. The hydrogen, which is the white one, is in the back, is wedged out, okay? It's wedged out. It's wedged out to you guys, right? This white hydrogen. But from my perspective, because I'm opposite to you, right? This hydrogen is what is dashed into the paper. It's in the correct position to assign, right? Which means you don't necessarily need to rotate. You just need to assign as it is. Because the rest of them, for example, if from your perspective, it's clockwise, then from my perspective, it will be counterclockwise. Does that make sense? So you don't have to flip the molecule. You can just flip R and S. So that's only the case where your least priority group is wedged out. Because I see the different R and S from you. I can assign, from my perspective, if I do this, from my perspective is clockwise, but from your perspective is counterclockwise, the one that I'm rotating, right? So, but I'm seeing hydrogen in the back of the paper. You are seeing this hydrogen wedged out of the paper. So you don't, in the case of the second, okay, you can just assign as it is. So it's counterclockwise. It looks like S, but because your hydrogen is wedged out, it's actually R. So you don't have to do flip or rotate, as long as the least priority group is wedged out. So it's in the exact opposite assigned. Good? That's a small trick, yeah? Okay. And then some review. Enantiomers and diastereomers. Only if all the stereocenters are opposite to each other, they are a pair of enantiomers. But don't forget to check if they are identical, which means they are the same compound. Or they are meso, which means they are symmetrical plane. As long as one of the stereocenters are the same, they are a pair of diastereomers. All right, common mistakes. I've talked about this, I think, at least 5 times already. Forget to assign R and S in nomenclature. Common mistake number 2, assign this one. It's tricky that when people see wedge or dash, people start to think, I need to assign R and S. But if I want to assign, this one has to be a stereocenter first. Is this a stereocenter? No, because these two are the same. Okay, common mistake number 2, it's not a chiral center. Although we still draw wedge dash, but the place we draw wedge dash, it doesn't mean it has to be assigned an R or S. Common mistake number 2. People will somehow still assign, I don't know how, but they will. Okay. Common mistake number 3, which is the mistake I talked about last time. Okay, didn't compare neighbor by neighbor. Okay, so this was exactly the same example I used the last time, where I talked about although hydroxyl group has a higher priority, but because this carbon is bonded to 2 carbon and 1 hydrogen, this carbon is bonded to 2 hydrogen and 1 carbon. In the game of here, whenever you see a difference, the game is over. This carbon already win. Okay, common mistakes number 3. Jump the carbon next to it and directly go to the third neighbor for priority. No, whenever there is a difference, the game is over. Okay, so in our case, this is number 1, this is number 2, this is number 3, this is number 4. Although number 3 has a hydroxyl group. Make sense? All right. I have 18 minutes to do these 2. All right. So you should all have, maybe I should. Okay, so if you prefer to do it, I'll pass this one around. Okay, I have a bunch of colored flashcards. Okay, pass it around. So if you prefer to do it on the notes or iPad, that's your choice. But if you choose to do it with a real flashcard, so that's the one to make. So remember I showed you before my flashcard like that. So this is an example. That's I also labeled it here. Okay, I also labeled here. Lecture video, this certain amount of time. So which means I copy exactly the same thing from your lecture video. The point is, even I'm just copying it, I still see students copy paste from the answer. I still see mistakes. Okay, so this I will do the first flashcard with you together. So you have learned free radical coloration of methane, okay? And I told you before, reaction, which I'm writing in black, okay? The one that you guys were doing she was teaching in class looks like this. And there are conditions, and these two are products, okay? So I'm rearranging this a little bit, sorry. I'm rearranging this a little bit. So what are the mandatory parts of a flashcard? Okay, the name of it, okay? So that's the name. And a reaction, which you should have reactant, okay? Reactant. So that's the place for you to write reactants, okay? These are conditions. Conditions. The green parts you don't have to write, okay? The green part you don't have to write. And product, okay? Product. Ideally, you can label which one is major, but in this case, there isn't a major product, so it's fine. Ideally, label which one is major, okay? So all the green parts are the first name of a reaction. And the mechanism is the last name, okay? It's the last name of a reaction. All reactions have mechanisms. It's just a matter of do we test you or not, okay? I've mentioned that in the first discussion. In whole 118A, you have 21, sorry,
are the flashcards supposed to be blank?
Is there something writing on that?
Yeah, all of these have a lot of writing on it.
Oh, sorry. Okay, I probably passed around some of my own flashcards. Okay, thanks for whoever gathering this. But I'm running out of my flashcards. If you don't have, those are pretty cheap. You can get flashcards anyway, okay? Thank you. I'll get the rest of them. By the way, what was on that? Was that chemistry?
I think so.
Okay, never mind. Okay, I'll get it, okay? Okay, you will have 21 reaction with mechanism in 118A. Go make at least a 21 flashcard, okay? At least, which means you can, if she lists another example with the same mechanism, you can also make more, okay? Okay, mechanism. You can ask me questions or stop me whenever you want, okay?
Does the mechanism go on the back?
What?
Does the mechanism go on the back? Does anything go on the back?
I'm running out of the space, I cannot show, but you can put mechanism on the back, or in either place that you think works best for you, okay? Okay. Okay, so the first step, you probably have learned that this bond, this is a radical mechanism, right? So on your lecture slide, it's a single end arrow. It's a single end arrow, okay? Well, I know your lecture slide is black and white, okay, but this is under H mu. So my habit, I want this to become your habit as well. Label the electron with the color you draw for the arrow. For example, if I draw red for single end arrow, this bond was consist of 2 electrons. So each electron go with the atom. So actually there are 2 of them, but I just draw one. So it's actually these 2, okay? These 2, okay? And the second step, okay, hydrogen. So pay attention to this one. Because one of the electron goes to the carbon. So I start with the bond and with the carbon. I see mistakes like this. So this is not correct. So the green one is not correct. I see people do this. Green is not correct because this radical finally goes to carbon. Okay, if you come back to her slides, she drew it in the exact way. But if nobody has told you before, you might get lost, okay, and make small mistake like this. That's why I do the first several flashcards with you. Then the rest of them you should have good habits on, okay? Now I'm making this bond in yellow, so the red radical with the chloral is going to come back here, okay? Maybe I rearrange this a little bit. Okay, I just leave it like that. It's fine. Okay. My CH3 is going to have a yellow radical, and the other side is hydrogen and chloro. They are forming a yellow bond. Okay. So you can stop me if you have questions. All right. So here comes to another chloro. Okay, chloro. So I will label with a different color. This time it's purple. Okay. And my CH3 with the yellow radical in the previous step is coming over. All right, so this yellow radical is going to form a bond with the chloro. And this bond is purple. Okay, my chloro has a purple radical, and my chloro and CH3 has a purple bond. I think that's kind of clear so far, right? And the final is termination, which means whichever radicals you have. So how many radicals I have? So the red chloro, so I'm duplicate, and yellow CH3, so that's another pieces. And what are others? Okay, I only have 2 different kind of radical pieces. Then it's the combination between these 2 pieces, okay? So this one, if I duplicate, okay, duplicate, okay. So because we throw the radical all pieces in the same flask, as long as there are pieces, they can, so I only have 2 radical pieces. They can do any combination they want, okay? So they can do any combination they want. Okay. I will add up their colors afterwards. So I'll use a color I haven't used before. Orange, okay. So now this is the termination step, okay. Because this is a radical reaction, so all of the arrow are single end arrow. Later, you are going to learn arrow with double end, which are ionic, so the transferring of a pair of lone pair. But this one is a radical, so it's a single end. This is also part of the review for your midterm 1. But from my perspective, it's the first flashcard you made in the organic chemistry. I do the whole process with you. In the future, you do it on your own. Good? Okay. I still have 8 minutes. Maybe, okay. Why do we make flashcards? Because we want to make reaction map. Now you have unlocked chapter alkynes. Sorry. Yeah.
In the second step, the CH3 and hydrogen separate,
yes,
form radicals, and the Cl immediately bonds at this stage. I think it doesn't make a difference here, but in another reaction, couldn't the H radicals go on to mix with anything else?
Yeah, it can be. It can be. Yeah.
Okay.
Yeah.
So it's not like that step actually always happens.
Yeah. So this we are showing the process of this one, but it changes if it's other. Okay. Well, any more questions about this mechanism? Although I only use one example, which is the example that you are using from your lecture slide. If you go check the timeline that I was showing here, she was printing out this exactly. But if I need to, let's say, for example, if she puts a mechanism question of exactly the same reaction that she was showing on her slide, I was just copy, paste, and I told you there are a lot of small things you should pay attention to, right? Single end arrow, and the position of where the arrow ends. Those you might lose points on that. So even you are copy paste from your lecture slides, you still lose points. That's why I want you guys all generate habits from now on. Drawing all mechanism correctly. As long as you know the mechanism, you don't lose point on it. Good? All right. So yeah, so I print this out, I give this to you guys. now you are here, right? Alkynes. You actually, now that's the first city. Maybe chapter 4 or 5, but anyway, it doesn't matter. Now you have learned alkyl, so this one, what's this? This is alkyl halide, right? Hollow alkynes, okay? Halogenation of alkynes, so it's hollow alkyl, or alkyl halide. So I'll use Rx, okay, Rx. So now you are starting to build your city, chapter 6 and 7, okay? Chapter 6 and 7 is going to be the reaction of alkyl halide. You just build the first round on your mechanism map, right? Which is the halogenation, right? I'll change into a thin pen. Okay. So your first, okay, halogenation of alkyne. And that's your first flashcard, right? Starting from now on, I told you there are 21. Reaction with mechanism. Put them on the map. That's the first round. You will have 21 more. Of course, I didn't draw 21 rounds here. It's your choice. And you can choose which circle to be which city. Okay? Good? Maybe I will just, I personally unlock the other one here, so you have a better idea. So this one is alcohol, which is the chapter 8. But that's something you should worry in the midterm 2. Okay? So basically, although you guys haven't taken the first midterm, but I already plan ahead for you guys for the midterm 2 already. So build your routes during the lecture with the flashcard. Okay? Sounds good? All right. I didn't upload the video 3 because I was super busy last week. I was making your midterms. I was editing it. I was editing the video. So before I left my office, there are 1 hour 4 minutes left. So it's on it. So hopefully I will upload the video 4 on time. I hope. Okay. Any more questions?
Yes.
Yeah.
So for the mechanism, is it just those 6 reactions that we need to know for the mechanism?
Which?
For the mechanisms that we wrote down, is it just those 6?
Just this 6. For this one, it's just 6. But
Yeah.
if you change the example into something like CH2, CH3, or CH3, so and then with chloro, that's going to be a different mechanism, but it works the same. Okay. Any more questions? We still have 3 minutes until 7:10. No? Do you want to spend the last 3 minutes review? Oh, yeah, question.
Is stereoisomers coming for the midterm?
I think so. Yeah. Okay. Do you want to still review a little bit for your quiz? Or so I will start handouts at 7:10. Now it's 7:07. You want or you can ask me questions? Okay, I will project the field note. Although I'm uploading this, but if you want, you can just see it. So. No, it doesn't allow me to. Okay, so okay. You still have 2 minutes, okay?